Okay, sleep whole day in Puja vacation. Didn't go out. Just wait. I got more. Okay, permission nahi hai. Okay. Anyways, so welcome everyone after your Puja vacation. I hope you enjoyed at home. Fun. I didn't go anywhere. Wow, tripod গৈছিলা. Boy. Okay, so today we will see two topics. One is binary search tree and other is AVL tree. Okay, let me just share my screen. So today we will see binary search tree and AVL tree. Binary search tree is a very popular tree actually. Uh, Last classes we have mainly discussed about different types of binary tree, and in those type of binary tree most of them are like either full binary tree, complete binary tree, mostly related to the number of leaves and height and all, correct? So in case of binary search tree, wait, is the meeting long? No. What happens? It's also known as ordered binary tree. Why? Because it follows a certain rule. There are three main rules. The root node means there will be a root node. Then from there, your right subtree will be greater than or equal to your wait. Okay. So if it is your root node, then your left all the nodes at left side or left subtree will be less than the root node, and all the nodes in the right subtree will be greater than root node. So it has three properties. All the nodes of left subtree are less than the root node, and all nodes of the right subtree are greater than or equal to the root node. And both subtree of each node are also binary search tree. That means all these nodes will follow the same thing. Suppose in this case 30 is your root node. So if you see all the nodes in the left side are smaller than number 30, 7, 15, 22, 17, 27. All are less than root node. And in this side you can see 60, 45, 75. All are greater than your root node. Okay. So now again come to this node. See 15. Now left subtree it's 7. 7 is less than 15. Again see 22. 22 is greater than your 15. Again come to this point, 17 is less than 22 and 27 is greater than 22. In case of 60, it's 45 is less than 60 and 75 is greater than 60. So there is no like means it has to be height of this type, lymph nodes, and no restriction in that. Is that it should follow this condition. All the nodes in the left subtree should be less than your root node, and all the nodes in the right subtree should be greater than your root node, and all the nodes will follow the same rule. Is it clear?
Yes,
If
ma'am.
we okay, it's waiting at the okay. So can you tell me what will be the advantage of this type of binary tree?
If we
If
need
we
to search something that is greater than the root node, that we have to find it only in the right side.
yes, that means it will help you in the searching, and in searching will be lot faster because once you know the key sorted. Yes, it's true. Shorting is time efficient, then even searching will be easier too because suppose I want to find 15. Then what you need to do, just need to check the root node first. Then you compare the key, the one you want to search for, and the root node. So if the searching element is less than your root node value, that means you will only search in the left subtree, correct? You won't go to the right subtree. It's like your binary search, right? It's kind of divide and conquer approach if you use binary search tree. So your searching should take log n time because you are completely discarding one half, and based on the root node you can say your root node is the middle one. If you compare with the binary search means searching technique, so it's kind of similar. In binary search we divide an array into half, then either we go to the left half or the right half, right? So same thing in case of binary search tree, we just check with the root node. So if number is greater than the root node, we go to the right side. Otherwise, we go to the left side. Okay, complexity I'll show you later. Now, suppose you want to uh, create a binary search tree. How will you create it? Suppose we have numbers. First questions might be like this. Means in competitive exam also. So anyways, suppose these are the nodes I'm giving or numbers I'm giving, and I am asking you to create a binary search tree. Okay, what should be the rule? First, you always go from the start. Okay, so you will just insert this 43 into the tree as the root node. Okay, 43 is going to be your root node. This is the first item you are seeing. Then I have to go to the next. Now I have 10. Correct? Now you tell me 10 is, wait, I'm getting forward. Hello. Okay, now we have 10. 10 is greater than 43 or less than 43? it's less than 43, right? So it will come to your left subtree. So it will become the root of the left subtree, correct? Next, we have 79. 79 is greater than your 43. So it will come to your right side. Okay. Now we move again. Now I have 90. Now see, 90 is greater than 43. So of course it will come to the left side. Now again in 79, 90 is greater than 79. So it will follow the same BST rule and we will just add it into the right side. Correct? Okay. Okay, sorry. Now we have number 12. Now see 12 is less than 43. That means we have to add it in the left subtree. Now again 12 is greater than 10. That means what? For node 10 we have to add this 12 into the right subtree because we have to maintain the same BST rule. The right side should be greater than your root node and the left side should be less than your root node. Correct? So next we have 54. Now 54 is greater than 43, so it will come to the right side. Now 54 is less than 79, so we will add it here. Next we have 11. 11 is less than 43. Now you come here. It's again greater than 10. So it will come to right again. Now 11 is less than 12. So we will add it here. Okay. Now we have 9. Now 9 is less than 43. Come here. It's less than 10. And it's this side should be greater. So we won't go to this side. We will simply add 9 here. Correct. Now we have 50. 50 is greater than 43. So we move to the right subtree. Again, it's less than 79. So we will come to the right side. Okay. So again, in right side, we have 54. 50 is less than 54. We will add it to the left side. Is it clear? How we can create binary search tree?
Yes, ma'am.
Yeah. First number, you can just take it as a root node, then you just go one by one sequentially and check the property, and accordingly you will keep adding the numbers in the branches. So if number greater than the root node, go to the right side. Same rule will be followed in all the right subtrees and each of the node. Okay, and if less than, then it will go to the left side. Is it clear to everyone? Clear, Dula said clear, Dula clear. Okay, yeah. Okay, now suppose I want to add one more item. say 100. So 100 I'll put where? I want to add 100. Left. Left of what? Left of 90. Is it left of 90? Yes, it should be right of 90 because 100 is greater than 90. So greater elements will go to the right side. Less elements will go to left side. Is it clear? Now suppose I want to add one more item, maybe 8. 8 will be added where? Left of 9. Yes, correct. Will just come here. Okay, left of 9. Yeah. So this is all about my memo, echo show, one screen when blank, screen and yes. Same. Okay, maybe network connection. Wait, I just unshared and share again.
Back again.
Share again. Dular ka clear hai. Can you see it now?
Yes, ma'am.
Yeah. Okay. So suppose I want to, okay, I guess insertion is clear to you guys. So whenever you need to insert something, you just need to see whether it will go to left or right, and accordingly you will simply add the item. Okay, so this is simple. Now if you want to delete the item, what will be the case? Suppose you want to delete 11. Okay, 11. What you will do? It's very simple. This is case 1, you can say. Okay, case 1, delete 11, and 11 is your leaf node. So there is nothing connected to the node 11. That means you can simply this node. Okay, you can simply this node. Okay, you can delete this node. Right. Now suppose you want to delete this 90. Okay, now I want to delete 90. Okay, what will be the case? Can I directly delete 90?
Did 100 and then 90?
Ma'am, first 100. No, if I want to delete one item, you cannot delete any other item. The rule will be different. If you want to delete 90, then only this one should be deleted. This one won't. So in this case, what you will do, you will see what's the children of 90. So there is only one child, that is 100. Correct? So what you will do, if you want to delete it, you will simply copy the value of 100 here. Okay. So your newly formed and you will cut this one and override it as 100. Then this node will be deleted. So what you are going to do to delete this, you will copy the value of 100 here, then you will remove this node and will just write 100 here. Okay, so your 90 node is deleted and your BST rule is still same. 100 is greater than 79, correct? And rest is still same. Okay, so in this case, always see what is the successor or the child. Then you just need to copy the value of child here and you can simply delete that node and replace the value of the child in this node. Okay. Then suppose you want to delete something from, okay, suppose there are some more elements, maybe 11 is already there and here is also an something here. Never mind, just think it's 13, okay. So now you want to delete this 10, okay. Now you see you have to 10. Now if you want to delete 10, just think what are the things you need to check. You cannot simply delete 10, right? You have to take care of other roots, and other child means is the root of whole left subtree. If you are going to delete this root node, there should be a replacement, correct? So in this case means if you want to just delete something from the middle and which is just your root node, your tree can be bigger than this one. Just remember whenever you are going to delete any node and it has like two children, in this case you just need to replace it with the in order successor. Okay, you replace with the in order successor. In order successor means what is the in order way, how we calculate in order. Will replace 12 will replace, no, if you replace with 12 then see 11 is less than 12, so it should not come to the right side, right? 11 should come to the this side, left side. So 12 you cannot replace. So you just need to find the in order successor. How we find in order? It is left, root and right, correct? So if you follow this in order process, what will be the value? Just start it from here. So we will go to 10 first. Sorry, for 10 it will be 9. Again for 9 it will be 8. Correct? So it will be 8, 9, 10. Then we move to the right side. For this node it's 11. So your in order successor here is 11. So what you are going to do, you are going to just replace this node with 11. So you just copy the value of 11 here and you simply delete this node. Okay, so if you delete this and replace it with 11, that means this node is gone. Okay, but it's still following your BST rule, correct? How? See 11, this left side you see it's 12. 12 has another children which is 13, which is again greater than 11. And this side all are less than 11. Okay. So if you need to uh, delete something from the middle and it has like both left and right subtree, just replace that node with the in order successor. So you just need to check which node will help you to maintain the essence of binary search tree. Because for all, 12 you cannot. Why? I told you 11 was there. If you replace with 12, 11 will be less than 12, correct? So suppose the 11 was here, right? 11 was here and here it was 10. So you wanted to replace with 12. Okay. So if you want to replace with 12, then what will happen? It will connect to here, suppose. And the 13 will be here. 13 is still okay, but 11 is less. And this 11 should be in the left side. Correct? Are you getting why it's 12 cannot? It will break the rule. 11, it's if 12, this 11 should come somewhere in the left subtree, not in the right subtree. But if you do that, it's not going to work out. You have to put it somewhere else. So you always put in order successor. So you just check what will be the in order successor, means left root right, you just check it, then 11 will be there. So after 10, if 11 is there, so if you just replace with 11, then it will just simply keep the essence of your binary search tree, right? You just need to copy the value of 11 here and put it there. Now rest is all same, no problem at all. Is it clear? Okay, good. So let's take a small one. Suppose it's 8, 3, 6, 1, 4, and 7. Now, if you want to delete something, okay, see this here I have written 8. Okay, 8 can be in the right. Why? Because the condition is in the right subtree, all the nodes can be greater than or equal to root node. So same number can exist in the right side of your tree, right subtree. So here I have just inserted 8, which is still valid because this data is just equal to 8. Okay. Now in this case, suppose you want to delete 3. What will be the replacement value for 3? How can you delete node 3?
4.
Yes, correct. So the in order successor will be 4. If you go root, left, right, and then again right side again same 4. This is in order successor 4. So if you keep it 4 and you just delete, so it will just still maintain the BST rule. See, all the values after in the right side of 4 is greater than 4 and in the left side it's less than 4. Okay, so this is all about DST. So what will be the time complexity? So for search, insertion and deletion, best and average case will be log n because we always just go to either left side or right side. But worst case will be n. Okay, and the space complexity will be O n. Why n? Because anyway you need to store all the data there. Okay, so searching means if you want to search for an item which is in the last, maybe the last right side of the again right most node, then of course it will take n times. So same thing will also applicable to insertion and deletion. So best and average case is log n, and worst case complexity for binary search tree is on. So it's just like your linear. Even in binary search algorithm for normal searching is also on for the worst case. Okay, so BST clear? Okay, BST application. So BST binary search can be applied in various dynamic sorting because you already told that it's already sorted manner. So it's very easy. So then for managing virtual memory, then multi-level indexing of data is they use binary search tree. So binary search tree is okay, understood? Not so tough, right? So BST is the most popular one. So after that, most of these binary tree or tree data structure follows the BST rule. That means the root node will be the okay, for heap it will be different anyways, but rest it will always maintain the BST one. So what is Avl tree? Okay, Avl tree is your height balance tree. Remember in binary tree we got one balance tree. That was what was there in balancing tree. We had a balance factor, right? And the height difference should not be greater than one. Okay, uh, better than one or two. So in AVL tree, it is also balance tree. It's a self-balancing tree, and its balance factor can be either -1, 0, and 1. Okay, and if your tree is unbalanced, then we need to balance it out. Okay, and your balance factor is calculated height of the left subtree and height of the right subtree. So let's see. So in this tree, you can see for this node, your balance factor BF is 1. Why? The height of your right subtree is 1, 2, 3, right? And 3 minus here it's 2. 3 minus 2 is 1. Again for the node 50, it's 1 minus 2. Why? Left subtree height is just 1 and the right subtree is 2. So 1 minus 2 is minus 1. And for this, it's just 1 child. So 1 minus 1 is 0. Again for 75, 1, 1, 0. So for the leaf nodes, balancing factor is always 0. Is this clear? It's all about just balancing, height balancing, balance factor. So balance factor, you can calculate left subtree, height of left subtree minus right subtree. Okay. And if the balance factor is not -1, 0, and +1, we need to perform certain operations. What are the operations? It's AVL tree rotation. So AVL tree, since we need to maintain the balance of the tree of each node, we need to perform certain rotations, and therefore there are four types of rotation. One is left rotation, one is right rotation, one is left right, and one is right left. Okay, so this left rotation and right rotation, these two are your single one, these two your single rotation, and these two are your double rotation. So first two are comparatively easier and the last two are slightly different. So this avial tree is named by the inventor Adelson, Baliski and Landis. So three inventors. So name is avial. It is key and Landis. So A, B, and L. Okay. So is this one clear? AVL tree. So why we need AVL tree? AVL not clear. Okay. AVL is just height balancing. Okay. Okay. It has a balance factor. Okay. Balance factor means will be height of left subtree minus height of right subtree. Now why we need AVL tree? AVL, I just told you the name came from the tree inventors. Okay. So AVL tree controls the height of your binary search tree, because just think you are just adding the items in like normal way in a BST. Suppose you're just adding things like 42 means arranging in a sorted order. Okay. 35 you are just keep adding. Okay. Then 14. Remember, we also learned about skew tree. Okay. So skew tree is not exactly desirable. So if we just keep means sort any item in a BST either in ascending or descending order, then what will be the result? It will be a skewed binary search tree, right? And we don't want that. Okay. So we need a balancing technique, and therefore these three inventors just suggested AVL tree. Okay, so AVL tree will simply balance out your binary search tree. See the time taken for all the operations in a binary search tree of height OH. Okay, means if it's a skewed one, if you keep adding things in ascending order, it means sorted array, not array means all the nodes in a sorted manner, then it will be a skewed array. So in this case, all the operations will take OH time. That means which is directly proportional to the height of your BST. So now we have to make it a bit easier. Means we want that all the operations should be in login time also. Okay, so just to get this login time, we just need to balance out the binary search tree. Okay, and therefore we have, okay, so in this case, what is the balance factor? Height minus left minus right, it's 1, 2, 3, 4, right? 4 minus here 0, nothing, 4, which is not desirable. So in AVL tree, your balance factor can be minus 1, 0, and 1. That's only desired balance factor in a binary search tree or binary tree. Okay, it's mainly because for binary search tree. So to maintain this binary balance factor, we need to perform certain operations. See here height is 4 and we don't want that. Balance factor should be either minus 1, 0 and 1. So we have to perform certain operations to make sure all the nodes are nodes having like this type of balance one. Okay. So for suppose 40 10, 50, 11. Okay, what will be the balance factor for this node? For 40, what will be the BF for the root? What will be the balance factor? 0. No. For left is height of the left tree 1, 2. 2 minus, yes, 1, 2, 3 is minus 1. For this one, 1 minus 1, 0. And for this one, it will be 0. For 50, it's 1 minus 1 and 2. So it's minus 1. For this one, it's 0. For this one, it's minus 1. For this one, it's 0. So this is already maintaining the balance because the balance factor for each of these node is either 1, minus 1 or 0. Okay. So if I add one more 100, what will be the balance factor of this node now? If I add one more here, 2 minus 4 is minus 2. Okay. And we don't want that because the property of AVL3 is that balance factor should be in this range only. So whenever your balance factor is not within this range, then we need to perform certain rotation operation. Okay. So this is not desirable. If you find that for any node balance factor is 2 or minus 2 and more than that, we have to perform certain operations so that balance factor become like minus 101. So the main condition is balance factor for each of the node in AVL tree should be in this range, minus 1, 0 and plus 1. So in the next class, I'll show how we can perform the rotations. Okay, I already mentioned there are 4 rotations. We will discuss about that in the next class. Anyway, it's going to end. I just take the attendance. Is it clear? The basic of AVL at least? Okay. Binary search tree should be clear too. Okay, I have taken your attendance. Okay, so I guess BST, binary search tree, is clear to everyone how we can insert, how we can create a BST, how we can insert nodes into the BST, and how we can delete a node in BST. I hope these three operations is very clear. And for AVL tree, it's just about balancing factor. It should be in minus 1, 0 or 1. Then if it is not the case, then we have to perform certain operations and we will discuss it in the next class. Okay. So, so I end my today's class. Thank you. See you in next class.